Hey guys, how are you? So let's get this done also. So welcome to the Packers and Obfuscators class. This is gonna be pretty cool because basically here, guys, we're gonna learn techniques to deobfuscate malware and .NET malware, but manually, guys. Keep in mind, our vision in Hack Defender is to teach you by hand. We don't want to teach you tools for you to just double click and get it dumped from memory and that's it. That's not the case. You need to understand from scratch and then you automate it. So let's get it started. Okay, so let's start with the agenda. So we're going to be talking about useful tools, for us, so that these whole slides are ready for you to go into the lab. Useful tools for deobfuscation and unpacking. We're going to talk about a strategy called Carnita methodology that is one of the techniques that I have been doing since I started doing malware analysis back in 2000 something in Semantic, which is a technique that always works for me, so I definitely want to share with you guys. We're going to be talking about .NET obfuscation tricks. It's very important for you guys to know those tricks that the malware uses in order to hide, in order to, make it harder for you to understand while doing the analysis. Because once you know those tricks, when you are doing your analysis, you will be hunting for those tricks. Like, for example, if you know that the malware is using assembly.load in order to in order to load an assembly in memory, and then you can dump it from there, you will be hunting for those assembly.loads in your next analysis, right? So the more you know, the more indicators you have in order to have a better result. Then, very important, guys, you're going to be learning automated ways to deobfuscate .NET. So that, once you know how the malware works, once you know the exact point where it is loading the malware in memory, you can automate it. The process is always do it manually, understand it, and then automate it. Otherwise, it's not scalable, right? So dozens, hundreds, or even thousands of malware comes every day to your queue. You cannot pretend to do everything manually, right? You need to automate it. And finally, lab time. These slides are just for you to be ready for our lab. Okay, so let's talk about the useful tools. For traditional Windows binaries, and by traditional I mean the normal C compiled binaries that just go straight, into the assembly. So that's what I mean by traditional ones. So we're going to be using, as you know, IDA Pro, the free version, which is the version 7.x, which is a debugger and disassembler. The good news, guys, is that this version is good enough for us to do the labs. And also, you are going to be able to replicate it. If suddenly, not suddenly, if eventually you get hired as a malware analyst, or you will definitely know that your employer is going to pay for that license. It's very expensive, around 2,000 plus. And but don't worry, if you are a malware analyst, you will definitely get a license for you to use. Okay, so this tool is able to disassemble x86 and 64 Windows binaries. I'm talking about the free version, right? It cannot disassemble, for example, ARM or other architectures, but for us it's enough, which is the different versions we're going to be using. It comes with a debugger available, which is also great because sometimes, depending on the architecture, it doesn't have the debugger, but for Windows binaries, it is available. So that's great. We can also document our findings into the IDB. The IDB is a database that is used by IDA so that it can store all your documented functions, parameters, everything that you learn of the malware behavior, you can store it in an IDB so that you can load it all the time. Easy to follow execution flow. One of the main advantage of IDA is this graphic flow, because normally when you are debugging in a traditional GDB, WinDBG, Immunity, OliDebug, or call it Jydra. By the way, Jydra, I don't know if it has debugger. I don't use it. But those debuggers has all the instructions in a sequential order, one after the other. But that view is very hard for you to know. For example, if there is a loop, it's very hard for you to understand the flow, right? So just a single loop sometimes is very hard to understand, right? Sometimes you are in the address 40.20.20, which says jump to 40.10.10, and then you jump there, and then suddenly you keep doing a lot of, a step into, which is executing every single command in the debugger. Eventually you reach again the 4.20.20 address, you jump, and you do that for the next 10 times. Eventually you realize you are in a loop, which, the debugger has these arrows showing you that you are inside a loop, but still it's not like pretty good looking. So that's a simple example of how hard it is for you to understand the flow. So in IDA, with the debugger, you have this fantastic view. Now, that's for Windows, right? But for Linux or ARM, for example, what I really like to do is, you can use also IDA debugger, but you can use WinDBG or GDB. So my recommendation is always to use IDA for the flow identification statically, and then the debugger wherever you want to use it for the dynamic execution, right? That combination is the recommended one. So this flow is huge for us to understand, and I'm going to tell you why we need to have a quick view of the flow by once I explain the Carnita methodology. Scylla is an import reconstructor. By import reconstructor, I mean the import address table reconstructor. As you remember, the import address table is basically the section in the binary in memory where all those DLLs are being loaded so that the binary can know where to find kernel 32 NTDLL, where to find the kernel 32 create file API, right? So those import address table normally get damaged or get destructed, or it gets destructed when you have a packer. So basically, when the packer unpacked, the binary in memory, that import address table is destroyed. Okay, I said destructed. I don't know if that even exists, but well, basically it is destroyed. And when you dump it, you really need to fix the import address table. And you can do it manually, but doesn't make sense to do it manually, right? There is many tools, and this Scylla tool is really great. So kudos to Scylla creators, which is basically an upgraded version of the famous impreg or chimpreg. I used impreg probably 15 years ago in Windows XP. It was pretty cool. And this tool is actually based on that, but now it supports Windows 7 or Windows 10 64 bits. So actually I'm using it in Windows 10 in our labs, and it works like a charm. So it's pretty cool. Another pretty cool feature is that it comes with the dumper module. So normally back in the day, you need to dump the binary from memory in your debugger, normally by using a plugin or doing it manually, wherever you want to do it. And then you use impreg in order to fix that dump. So you need to use two tools, and sometimes those plugins, doesn't work in the latest version of your preferred debugger. So it is a problem, right? But in this case, the module comes into the same tool, so you don't need to worry about other plugins. It's actually pretty cool. and it comes with a flavor for x86 or 64-bit version. So if you want to dump an x86 thread or 32 bits binary, you use that version, or you use the 64 one, which both works great. So kudos to those guys also. Now, for .NET binaries, we have dnSpy, which is a .NET debugger and assembly editor. We're going to have a lot of exercises in dnSpy so that you can master the usage of it. I really want to say that there is a history before and after dnSpy. So dnSpy came out around April 2016, if I remember well. And before that dnSpy, it was really very hard to do the analysis on .NET. You need to use different separate tools, or you have commercial options, but not very good, to be honest. And even people focus on MCL, which is this Microsoft Intermediate Language or bytecode, to do the analysis. But after dnSpy, to be honest, guys, at least in my experience, few times you need to deal with MCL. Most of the deobfuscation that I do with dnSpy is enough. Sometimes with dnSpy and other tools that I'm going to show you is enough. So kudos to dnSpy, guys, because also it's free tool. It's just amazing. And dnSpy actually comes with already software being used in the wild, like iSpy and many other ones. Is already tools that were there in the market, open source or free, but it just, get everything together and work is really cool. Okay, so dnSpy allows you to debug in the source code, right? As .NET, as you know, you can disassemble from the native code back into the MCL code, which is the bytecode, and back into the source code, which is pretty cool. And that's the reason that, because you can get into the source code, the malware authors put a lot of effort into protect .NET, because if you can get the source code of the .NET, you don't have assembly. You just straight start learning the code, and it's going to be easy for an analyst to get it done. It's pretty easy to dump assemblies from memory. If you get the blob of a binary, you just right click and save. That's it. You get the dump done. So it's pretty cool. It has a great feature to trace call stacks. Whenever you have any function, you can go all the way back to the main, so that you can know all the different calls being used during the whole execution, which is pretty cool. If you want to, for example, know that this assembly.load was called, who called it, and then from there who called it, so you can put breakpoints all in those different places, and then have a full understanding of the flow. Inline recompile of binary, since you don't need to have the source code for .NET, but you can patch it, hot patch. So you have the binary in source code, and then you want to remove a specific check that the malware does for a, let's say, virtual machine identification. You just remove it, recompile it on the fly, boom. You don't need source code, you just patch it right away. Easy than patching assembly, right? So it's pretty cool. Or you can put in a specific write function, to dump something from memory, or to put some printfs, to get more help in the debugging strategies. I mean, you can just edit and recompile. The second tool, pretty cool, is called Son of a Strike. SOS is a debugging extension for WinDBG created by Microsoft. And basically this tool allows us to debug managed programs via different breakpoints. So as you remember, managed programs in .NET are those programs that once they are compiled, they get into this MCL or Microsoft Intermediate Language, which eventually via the just-in-time compiler, they are transformed into native code, right? If you don't remember, by the way, if you don't remember how this works, please check the Windows binaries class where we explain this in full detail. So basically what the source helps us is like an interface between the managed code and the native code. The native code is this assembly, C-like assembly that we all know and we love. So this layer of managed code that the debugger doesn't understand is where source comes into play. And then, for example, we can say, you know what, this specific malware has a class called ABC, which has a method called create. So let's say dump malware. So you can put a breakpoint on ABC dot dump malware, enter, and then that's what is called deferred, because even though this class is not even loaded in memory, or let me put it in a different way, even though this class is not even being processed by the just-in-time compiler into native code, once we put the breakpoint, as soon as this class is called, the breakpoint is going to hit. And basically what that means is that we're going to stop exactly where is the native code related to that abc dot dump malware method. And that's the connection that we can do. So that's pretty cool, because then we can put a breakpoint, for example, in assembly.load, break there, and then dump the binary from memory in one shot. We'll see that in the lab. As I said, easy to dump assemblies from memory. This is not a source feature. This is more a WinDBG feature. Easy to do. Able to trace managed code stacks. Remember that source is all about managed code, managed programs, right? So when we do a call stack, you know, in order to know what was executed, so here is all about managed code. Which basically means we are going to see all the classes being used during the execution. In other words, we have visibility into the managed code, which is great. Okay, so let's talk about unpacking and deobfuscation strategy. Okay, so here is our famous Carnita methodology. So the goal of this methodology is to deobfuscate or unpack the binary as ASAP, as soon as possible. Carnita means meat in Spanish. Meat in reverse engineering context means malware code. Malware code is the carnita, is the meat, is what you really want to see. So you want to spend your time in the carnita, and not in the wrapper, not in the packer code, not in the obfuscator code, in the carnita. Do not fall into malware author's trap, right? I mean, they put a lot of effort protecting the malware to delay your analysis. I can see guys, and I did it, to be honest, at the beginning of my career, trying to understand the malware packer, trying to understand this obfuscation so that, you know, I can blog about it. Back in the day, 20 years ago, probably you need to understand those because you wanted to create a unpacker, you know, because it was everything was statically analyzed by the, you know, all those signatures based antivirus. But today, with the sandboxes and this dynamic execution and this instrumentation, I mean, there is no need to do that. You just get straight into the Carnita. Sooner or later, the malware needs to be deobfuscated in memory. Just wait for it and dump it. And let the real reversing effort start. Okay, the steps of the methodology is, first of all, quick understanding of the flow, right? I mean, you need to go quickly into the flow. You don't need to go into the details, but you just need to see how the flow goes. And then one recommendation is to identify if there is any empty sections in the malware memory space, and then eventually see if there is any decoder stop loops copying large amount of data into those sections, right? Like UPX. UPX has an empty section UPX0, and then all the data is copied from another section UPX1 into the section UPX0 in memory, and then it jumps into UPX0. So that kind of behavior is what you really wanna try to find when trying to deal with bug code or obfuscated code. The second step is, once you identify those sections, try to find dynamic calls or jumps into those sections. Because as I said, eventually, if this data is being deobfuscated or unpacked into a new section, and suddenly you see a jump into that section, that's a good indicator that you're getting close to what is called the OEP, the original entry point. As you know, the entry point is the starting point of execution of any program. The original entry point normally is called when there is a packer or there is a obfuscator, or this layer that first executes, and once it unpacks, then it calls what is the original entry point. In other words, the real entry point of the program or the malware. So this jump EAX, I call it dynamic calls. Well, it's called dynamic calls because this EAX normally is an address calculated at runtime. It's an address that is calculated based on the section or where the malware is going to jump next. Here's an example. So we can see that in the top we have these sections of this specific malware, which is packed with a famous UPX. UPX is very well known, and we can see that we have two sections here, right? So we have the UPX0 and UPX1. Normally in UPX, even though this is pretty simple, guys, please don't think I'm teaching you UPX. It's not the case. It's just to explain you the basic concept. So you can see we have UPX0, which is normally empty at runtime. UPX1 has the initial code, and eventually UPX1 is going to copy unpack data into UPX0 and call it. If we don't know this is UPX, let's apply the methodology. So first we identify this loop. We can see easily in IDA when there is a loop, and here there is a loop doing some shift left, eventually move the content of the address RBX to rags, do a B swap, which is just, swapping the less significant to the most significant bytes, and whatever, do some add. Again, we don't care about that, and we can see that at the end of this is doing a move from rags, whatever rags has, into the address pointing at RBX. These square brackets, guys, in the left side of a move is what you really want to look for in loops, because that means there is a real copy of data into a destination. Then you really want to see if this RBX, what it is. Is the stack? Is the heap? Is a new section? What it is? Which probably is, in this case, UPX0. So this loop, guys, is not like mandatory to understand it, but that kind of loops is going to allow you to know that you are very close to where there is a dynamic call. Because you can see, for example, in this case, that after that loop, eventually it's going to fall into the left side. And you can see that here is going to do a jump into 1400 AA3A. If you calculate this offset, you can check and see that UPX0 falls into that range, which basically means that eventually this specific code is jumping to UPX0. So that means that it's a dynamic call here going to this address which was filled out before. That's a good indicator that we are close to the original entry point. Here's another example. This is ASPAC. Again, we can see that in the left side we have this graph overview where you can see all the flow quickly with IDA. And again, I don't care about what's going on here or here or here or here. I don't care. I go all the way down and I see the jump EAX. This jump EAX, as you can see, is a dynamic call which is pointing to a place in EBP plus 7A, which might be a section, might be the heap, might be even the stack, but it's jumping there dynamically, okay? Which, by the way, this is ASPAC code, okay? So here is going to jump dynamically, and then we don't care about this whole flow. We just go there and jump. If we are lucky, after this jump, we might get into the original entry point, which basically means the Carnita. Now, the clever student might be asking himself, how do I know that when I jump into this AX, I landed into the Carnita, into the malware code, and not into another stage of obfuscation, right? So that's a very good question. So one of the recommendations is that when you jump into this EAX, check the address in memory, check if that address corresponds to a binary. You can go up and check if there is any MC header, which basically means you are inside a binary. That binary can be either a new binary loaded in memory, or can be the same binary loaded at the beginning, but with the modified bytes, which can be the unpacked code or the obfuscated code, and you can land there. A very good recommendation is that if you don't know, if you are not sure, just dump it, open it in IDA, and check if that specific section contains new instructions. Another good hint is that when you jump there, you might start seeing Windows APIs. You know, in this Packer obfuscation, you will see normally those memcpys, those memsets, you know, instructions, probably even load libraries to load DLLs. But you actually don't see normal instructions like connect for a socket, like create file, like, you know, rec open key for open the registry. So you don't see those instructions normally. So when you dump the code and you start seeing those Windows APIs, which looks like a normal code of instructions, and obviously if you see something like write process memory, which is a really kind of suspicious API, you will realize you are in the Carnita code. Okay, so those are hints. Obviously, those are not the only ones, but that can help you. And again, if you, for example, from this jump EAX, you cannot jump into a new place, and that place is just 20 bytes, right? It's just 60 bytes. Probably that's just another chunk, which is gonna decode another chunk. So every time you jump, you can dump it and see what it is there, and then decide whether you are already in the Carnita or not. So we're gonna see some examples here.